Hey guys, welcome to this video. Okay, today we're going to be doing the wave equation proof. We'll prove this bad boy. It's kind of like 3 in the morning, so you're gonna have to cut me some slack. I might zone out a little bit, and also I don't fully remember the proof by heart, so I've got like my phone here. But it should be pretty straightforward. So we have this. This is what this equation is stating. We have the position the acceleration in respect to time is equal to the wave speed squared times the acceleration in respect to position. Okay, so here's how we're gonna do our setup. Okay, we're gonna think of a string here. Okay, got little ends, right? And then this is x and this is like that, right? And like let's say, yeah, I've plucked this string, right? So that means I've got like my height positions, right? These are my positions u here, all along in respect to its x axis, okay? Now, here is our setup. How do I set this up? Yeah, we wanna zoom in here, okay? Let's zoom in on a piece of this string here, okay? We've got something like this. Ooh, that's a shit. Fucking nope. Okay, like this. Think of it like this, okay? If we've got these forces kind of tangent to the little things here, right? This is our tension, right? Our string's got tension. That makes sense. We've got T1, right? Tension 1, and T2. Okay. So let's think. What's a prime? What are we thinking here, right? We're thinking. Oh, where should I write this? F. No, I don't know the room here. Oh, that. Nope. Oh, let's keep this centered. F equals ma. Okay, it's true. It's a factual statement, but we got to think of each of the variables in this scenario, right? So we've got our force. Okay, what's the mass here? Okay, well, mass in this equation is going to equal to our linear density. Okay, linear density. That means it's density along some point on x here, right? Times some change in amount of x, right? That makes sense. Oh my god, like if I were to take like some initial point here minus this point here, right, I would get this x amount, right, that linear density, right? So this is our mass. What's our acceleration? Well, our acceleration is going to be I think it's in respect to position, right? So u is equal to height. Okay, let's remember that. U is height, and therefore, what is that shit therefore? Therefore, u of t is equal to acceleration. That being that, like if I were to take the derivative of u in respect to t, that would give me ut, okay? If I do this squared, that makes the second derivative, this utt, okay? So given this information, that means my mass, so that's my linear density times delta x times my acceleration utt. This is our force, okay? Oh, this is not the eraser I need. I need this eraser. Yes, sir. Okay. Now, thinking again of our forces, right? We have Jesus Christ. Yeah, our force is equal to tension up here. Makes sense. T2 minus this tension down here, right? T1. Oh my god. T1. Faker's team. That's crazy. Or, yeah, whatever. This should be fine. But here's the thing, right? We need to think of our... Oh, shit. Yeah. Let's take this like angle here. Oh, I should probably draw. Okay, right? So we've got an angle uh at this point, right? Angle theta. And we've got this other angle here. This is like angle theta plus delta theta, right? And what I'm trying to get at is we only care about the y component of these vectors, okay? We only care about these y components here, okay? The reason being is, like, when you're pulling a string, right? Like, these forces pulling, like, the string isn't really being pulled to the left and right, really, right? That's kind of negligible. When I pluck a string, it's vibrating up and down, not really vibrating left and right, you know? So, like I said, we care only about these forces here. So that means that our tension here, let me just, I'm gonna rewrite all this. This is way too much. This too. I'll rewrite our force principles here. That our force is equal to, yeah, I'll write this one. Rho delta x utt, right? It's also equal to our difference of forces, so T2 minus T1, or yeah, let's just say T1 minus T2, okay? This has a greater force in the y direction. So tension 1 sine of theta. Yeah, sine of theta, I think, right? If I need the holy shit, I'm like tweaking. Oh my god. Uh-huh. Right. Oh no, I was right. Okay, so my bad, guys. T2, top tension, bottom tension. Okay. Yeah, T2 times sine. Right, I think so. Yeah, if I were to take the cosine, I get the bottom. Sine, I get the top. So sine of theta plus delta theta, right? Minus T1. I'm sorry, guys. I'm tired. T1. And this is the sine component, right? We want, yeah, this is our vertical type shit, right? If we did this, right? This vector is cos, right? And then this would be sine. I think so. Yeah, yeah, looking at it like this. Sine, this is, yeah. Oh my god. It's like I just have to believe it for a second. Sine of theta here. This is at like what? Yeah, this is, yeah, this is fine. Oh, I gotta let my dog in. Hold on, guys. Come on, get in. Okay, back to this important stuff. Next step here, right, is like, okay, yeah, realistically, what do we do from here? This is when it starts getting good, okay? Bear with me. Tension, right? Tension is always going to be the same along a string, okay? That is a fact. We learn this all the time when you do the pulley questions, right, guys? Tension is the same along the string, unless it's, moment of inertia, but fuck you, right? So force, right? Our force here is now actually going to be equal to tension. And listen, I'm going to skip a step here. I'm factoring out these tensions here, okay? Because, like, what I'm saying here is T2 is equal to T1, right? So that means they're just equal to tension, okay? If they're both the same, right, I can factor it out, right? Like so, right, this is our tension forces, and then I'm just gonna boop, bop, delta theta, boom, minus sine theta, okay? It's real, trust me. The next step is my favorite step anyway, okay? Is the divide by cosine everywhere, okay? We are going to divide everything by cosine. However, notice that we've zoomed in so much, right? Right? We zoomed into this really small thing. That means that these angles theta, right, are, well, rather, I should do like this, really fucking small, okay? As a matter of fact, they are like approximately zero. It's called small angle approximation, okay? That means if I were to divide everything by cosine, right? If I were to divide everything by cosine here, it wouldn't affect anything because cosine, when I guess, okay, like I could write it like this, okay? I could write limit, right, as theta goes to 0. This is essentially what's happening because the angles are so small. Cosine theta is equal to 1. It'd be as though I was dividing everything by 1, okay? So let's look at that. Let's look at that. What if I were to divide this by cosine of theta plus theta, theta plus delta theta, right? And then this also divided by cosine of theta, right? And remember, this is this is just 1. This is just 1, right? That means nothing happens. It's all, we're Bing chilling, guys, okay? That means we can just go and write it as they are tans now. Tan of theta plus delta theta. Yes, plus delta theta. Minus tan of theta. Okay? Nice. Very nice. Next step. Next step. I'm going to erase this and give us more space because we're running out of space. Boop, 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 boop. I like using MS Paint more, I feel like. This is a bit more cleaner, but MS Paint was much more convenient. Tension of tan, right? Yeah, it was tan theta plus delta theta minus tan of theta. Okay. Question for the group. Question for the class. What is tan? What is tan of some angle? It right? It's in the word. It's tangent, right? If I have a circle, bada bing. Well, let's say I'm on the unit circle, right? Okay, horrendous. Unit circle type shit, right? And I've got some angle. Let's say like theta here. What's tangent at this theta? It's literally this. It's literally this. It is. It can also be interpreted as the change of rate at that angle, right? Right along that curve, right? Under that understanding, change of rate along this curve here, right? It's holy shit. It's the change of the x over the change of the y, okay? That means I can just write this as change of x over change of y, right? Tension times partial of u, right? That's the change in our y, right? Over our change of x. What's our x? Well, okay, theta is actually in respect to position. So now that we're changing it to this, is actually d by dx of u of x plus like delta x comma t, yeah, minus u du of x comma t, that's a theta, over delta x. Okay. No, this is the next step, guys. The next funny. Yippee. Oh, I'm gonna pass out. I'm about to fucking crash out. Okay. Delta rho, right? Of the acceleration respect to time. Right? This is force. This is also force. That means I can make them equal to each other. Okay? So that means I do it times. Oh, by the way, I'm moving this delta x onto the other side. Okay? Times t of 1 over small change in x of this, right? U of x over time of x plus small x t minus same thing x t, right, over like x, right, dx. So I mean, like, do I need to spell it out? Yeah, I do. Even I'm passing out. I'm having trouble figuring this out. Um, yep, yep. My bad, guys. I wrote it like a shit way. Like this. This is over dx. This is over dx. Now you see, so we have a function here, right? With some slight change in x minus the same function of just x. Right? I don't know about you guys, but like but bing boom ba bang, right? This is this is derivative proof, right? Limit of like, yeah, right? Oh, guys, it's our function at x plus some slight change minus that at the same point, right? Uh, Divided by a slight change in x. That's crazy. That's crazy. That means that our function here now, right? Oh, sorry, I should probably bring this to the other side, huh? Right? UTT. Remember, I'm looking for this, right? UTT is equal to this, guys, okay? Watch this. Tension over linear density is equal, or times rather. Um, yep. I think I think this is squared. No. Yeah, x comma t over, right? So this is actually the derivative of this, right? Which is equal, again, tension over rho. Uh, yeah, second derivative of position in respect to x. Okay, I'm gonna write it up here. So UTT is equal to tension over linear density of UXX. That therefore means that C squared is equal to tension over linear density, or rather C is equal to square root of tension over linear density. It's factual, guys. It's been proven. You're welcome. I'm probably gonna re-record this. This is a horrible take. I'm gonna go to sleep actually. Um, arigato, sumimasen. Let me fuck. Yep. Anyway, guys, yeah, I'll see you in the re-upload of this one. It's not shit. Thanks.